Welcome to this open source large language models module. Throughout this module, we will learn about different open source large language models, their differences, and which ones are the best. Although ChatGPT has made a significant impact in the world of technology, it is important to note that ChatGPT is not an open source model. This means that we cannot modify its source code as it is not publicly available, nor can we use it for free since there is a cost associated with using the model through its API. In contrast to proprietary models like ChatGPT, there are open source models available. These models offer several advantages over proprietary models, such as data privacy, customization, affordability, and democratization. When it comes to data privacy, many companies prefer to have control over their data, and are obligated to keep it secure without sharing it with third parties. Using ChatGPT can pose serious privacy issues because, as mentioned before, ChatGPT uses user data to send it over to a server for training the model and performing analytics to allegedly improve the code. This violates the privacy of company data. One of the advantages of open source models is customization. Open source models allow developers to train the models with their own data and even add filters to have control over their data. This enables us to personalize the chatbot with our information and optimize it for specific use cases relevant to the company. Affordability is another advantage of open source models. Open source models are freely available, eliminating the need for a significant investment in hardware to train the models. They come pre-trained, so optimization can be achieved with fewer computational resources, resulting in lower costs. Finally, open source models contribute to the democratization of artificial intelligence. These models, being openly accessible, provide opportunities for future research and development to address various artificial intelligence challenges. Therefore, open source models offer several benefits that proprietary models like ChatGPT do not provide. Additionally, integration is an important consideration. Many companies might initially think that developing an open source large language model is more costly since it requires investing in computational resources and specialized personnel. However, this is not entirely true, especially when there is intensive use of such models. A recent study conducted at the Institute of Information and Technology of the University of Madrid in 2010 examined a language model used for creating these types of models. According to this study, for a low range of daily requests, around thousands of requests per day, models like ChatGPT are more cost-effective than open-source large language models. However, for millions of requests per day, which are not a high number and easily achievable by a company, open-source models become much more cost-effective. This can be clearly observed in the graph. On the vertical axis, we have the cost, and on the horizontal axis, we have the usage. The orange bar represents open source models, while the blue bar represents ChatGPT. When the usage is limited to a few queries, the cost of ChatGPT is significantly lower than that of open source models, falling within this range. This represents the cost of ChatGPT, while this represents the cost of open source models. It becomes much more expensive to use open source models when the number of requests increases. However, for moderate usage of these models, we can easily operate within this range, where the cost of open source models and proprietary models like ChatGPT is similar. However, when these models are used on a daily basis, implemented company-wide and widely used by employees, the difference becomes significant, and the distribution is reversed. It becomes much more costly to use ChatGPT compared to the cost of developing and optimizing open source models. While optimizing open source models may require initial effort, their usage cost remains stable regardless of the extent of usage. On the other hand, the cost of ChatGPT escalates significantly as its usage expands within the company. Therefore, if sporadic use of such models is required, proprietary models may be suitable. However, for daily and standardized usage of these models, it is much more cost-effective to develop and utilize open source models. Now let's try to put some numbers to the cost of using ChatGPT. As we know, ChatGPT's API is paid and costs approximately 0.02 per 1000 tokens. Each token roughly corresponds to 3/4 of a word. So, if we process 1000 small text snippets per day, which would be around 500 words or 667 tokens, the cost would be $1.3 per day. At first glance, this may not seem like much, but what happens if we process 1 million documents like that every day? Let's remember that 1 million is not excessive. It is a normal usage scenario. In that case, the cost would be 1,300 per day because we would multiply the previous cost by 1,000, resulting in a daily usage cost of 1,300, which translates to approximately $500,000 per year. Therefore, when limited usage of ChatGPT is involved, the cost may be affordable. However, when normal and standardized usage is implemented in a company, the cost becomes exorbitant. In such cases, it is more cost-effective to train our own open source model rather than relying on ChatGPT. In this task, we will discuss the different open source language models currently available on the market. Today, some of the well-known open source large language models include Llama, Alpaca, based on Java, Vicuña, and GPT4All. For example, Llama was one of the first models developed by Meta and served as a starting point for many other models. Alpaca, also developed by Meta, is based on the Llama model. Then we have Vicuña, which is an improved model based on Llama. It incorporates conversations with users, and through these interactions, the Llama model was enhanced to create Alpaca. Lastly, there is the Java model, also built on Llama but with further improvements. Through conversations with users, the Java model was developed, leading to the creation of Vicuña. More than just a single model, it is a toolkit of functionalities to create and optimize our own chatbot. Next, we have GPT4All, a community-driven project and a model trained on a massive corpus of interactions obtained from assistants like ChatGPT. It is further trained with additional information such as code and chat data, including cover flow and various sources. GPT4All is widely adopted and can be easily used in a local environment. Another model is Raven, an open-source chatbot that produces results similar to ChatGPT. We also have Opt, developed by Meta, which stands for Open Pre-trained Transformer Language Model. Although not as good as ChatGPT, it has demonstrated considerable capabilities, especially in zero-shot or fused prompting scenarios where there are few or no examples available. Next is the Flam T5XXL model, which has been optimized with over 1,000 additional tasks. It undergoes fine-tuning to improve performance across these tasks. In these additional tasks, Flam T5XXL outperforms more generic models like ChatGPT. Here is a summary of some of the most important open-source large language models available today. However, the emergence of these open-source models is just beginning. In recent months, there has been a rapid development of new models, variants, and an increasing number of options that can rival ChatGPT in performance. Here are a few models distinguished by the type of license. They are all open source licenses, but some models can be used for commercial purposes, as shown on the right, while others are developed for research or non-commercial use. Additional models include Colossal Chat, which integrates the development phases used for ChatGPT, including reinforcement models. There are also models developed by companies like Databricks, such as Dolly, and its variants like Alpaca and Alpaca. Lastly, there are newer models like Faiss, Koala, Dalai, and Llama, which are not widely known yet. For those models that can be used commercially, shown on the right side, NanoGPT and OpenChatKit are options, although they are not widely known. Nano T5 is also available, and all these models can be used for commercial purposes. As we have seen, the emergence of new open-source large language models is just the beginning, and the options continue to grow. Which model is good? How much data should be used to achieve reasonable performance? These questions were addressed in research conducted by OpenAI and Google. These companies document several studies indicating that large language models with tens of billions of parameters started to exhibit capabilities comparable to human performance. In the graph, we can see the initial models with only 1.3 billion parameters, which did not perform well in terms of precision, represented on the vertical axis, regardless of the context or examples provided. The maximum performance achieved was around 5%. However, when we move from 1 billion to 10 billion parameters, the situation changes significantly. Initially, with a few examples, the performance still falls short, but as we apply fused prompting techniques, these chatbots improve their performance. The maximum performance achieved in these scenarios is around 25%. However, when we make a qualitative leap from tens of billions to hundreds of billions of parameters, the landscape changes considerably. Models can achieve performance exceeding 60%, comparable to human-level performance. These models can learn a lot from a single example. Therefore, among the different options of open-source large language models mentioned earlier, those with over 170 billion parameters can be expected to perform very well. Hence, one criterion to consider when selecting an open-source large language model is the number of parameters it has. Additionally, there is a useful tool that provides insights into the current best-performing open-source large language models. By following the link to the presentation, it redirects to the official benchmarking page where the results are showcased. The evaluation methodology employed ELO ratings, which allowed the users to vote on the model's performance. The same prompt was given to Model A and Model B, and users directly voted for the better one. Users from around the world participated in the voting process, covering different languages and prompts, resulting in the rankings. In conclusion, we cannot definitely state that one model is better than others across all tasks. However, we can gain a general idea of which models perform better overall, and then it becomes a matter of testing each model in specific tasks and selecting the one that performs best for a particular use case. In this task, we will delve deeper into the open-source large language models derived from Llama. Llama was the first model to emerge. After Llama, Alpaca was developed as an optimized version. Finally, in recent months, one of the most well-known models, called Vicuña, was released. Vicuña is also a model that originated from Llama. Let's start with the first model, the original Llama model. This model was developed by Meta, also known as Facebook, and it was one of the earliest open-source models to appear. It paved the way for many more open-source large language models. For many months, Llama was the most efficient alternative among open-source models compared to proprietary models like ChatGPT. Despite being smaller than many commercial models, Llama has surpassed GPT-3 standards in various benchmarks. However, while it is open source, access to Llama is limited to researchers and comes with significant restrictions for commercial use. If we visit the official Meta webpage, we will find the announcement for the first Llama model. Here, they provide information about the model, indicating different sizes with 7 billion, 13, 33, and 65 parameters. They share insights on the model's applications, such as protein structure appreciation, as well as potential risks associated with the model. They offer access to the original paper, which is available here. The scientific article was the publication introducing the Llama model. Additionally, there is an application form for access to Llama, redirecting to this form. As previously mentioned, the use of Llama model is restricted to search, meaning we cannot freely use it for commercial purposes. We can apply for access using the provided form, or alternatively, we can access the Hugging Face environment, which also provides instructions on how to obtain the model. It states that we need to fill out the aforementioned form to download the model weights. Once obtained, we can use Hugging Face transformers to construct and utilize the model with further instructions provided. If we prefer not to install anything, another option is to access the LM6 chat webpage, which we saw before. This platform allows users to evaluate the different large language models by testing and voting for the model they find works best. Going to the single model section of the webpage, we can find the Llama model. Selecting it, we can directly input a question to the used model. Let's test this model by making a request and seeing the result we obtain. Here we can see the response generated by the Llama model with 13 billion parameters, and we can observe that it doesn't provide a satisfactory solution. This particular Llama model, even though it is one of the more basic ones with 13 billion parameters, there are Llama models with many more parameters that are more efficient and perform better. In this case, we can see that although it can generate phrases, it doesn't fully understand what we are asking. Now that we have learned more about the Llama model, in the upcoming tasks, we will explore the Alpaca and Vicuña models in greater detail. In this task, we will learn more about the Alpaca model. As mentioned before, Alpaca is a model based on the original Llama model. It was developed by researchers at Stanford University and is an improved version of the Llama model, which is also based on the original Llama model. Alpaca was developed using over 50,000 demonstrations following the instructions of GPT 3.5. Researchers claimed that it produced comparable results to the OpenAI model. What is most surprising about this model is that it achieved very similar results to the OpenAI model. What's even more impressive is that it achieved similar performance to OpenAI but at remarkably lower development costs. It is estimated to have cost around $600 to produce and train the model, a significant reduction compared to the millions of dollars required to generate the OpenAI models. Like the Llama model, Alpaca is open source, although it comes with certain usage restrictions. It can be used for research purposes, but its commercial use is highly limited. More information about this model can be found in the publication released by Stanford University when Alpaca was launched. It states that Alpaca is an optimized model based on the 7 billion parameter Llama model, adjusted with an additional 52,000 demonstrations. The preliminary evaluation with a single instruction showed comparable performance to OpenAI's TX DaVinci 003 model. However, Alpaca is much more smaller and much more cost-effective to produce, with a cost below $600. Further details about the model and its training process are provided. Initially, a set of instructions was generated to train TX DaVinci, resulting in an additional 52,000 instructions. Using these additional instructions, the Llama meta model and supervised fine-tuning, the first Alpaca model was developed. Currently, there are many versions of the Alpaca model. The Alpaca 7B is the original model, but there are now many more models available. The preliminary evaluation is also discussed. It responds without difficulty to a series of questions. It even correctly writes an email when requested. However, the researchers acknowledge their limitations. For example, when asked about the capital of Tanzania, it provides the correct answer, but mentions that it changed in 1974. From then on, it was Dodoma, so it would not be responding accurately. It can also utilize incorrect information to answer questions as if they were true. More information is available, including access to a demo, optimization instructions, data generation details, and access to the model. If we visit the original GitHub page, we can find more details about the model and instructions on how to use it, including generating input data. All the information about the model is provided. Although initially believed to be a significant competitor to OpenAI models, Stanford recently withdrew its model due to reported hallucinations, security concerns, and cost issues. As the researchers themselves state in their publications, this model is not exempt from the limitations that many large language models have, such as hallucinations, fabricated information, or responding incorrectly. Nevertheless, the appearance of Alpaca represented a significant leap forward, achieving performance similar to DaVinci while drastically reducing the training cost of models. If we want to use this model, there are various ways to access it. By visiting Hugging Face, we can find multiple versions of the Alpaca model. As mentioned earlier, there are many variants available now. It has been extensively used and optimized to generate numerous variations. We also have the native model with installation instructions and download files. Alternatively, we can revisit the AMC's page and give it a try. Here we can see how to use the Alpaca model and even compare the performance of the Llama model with the Alpaca model, highlighting a considerable improvement. Let's request both models to write a blog about interrail trips and compare their responses. We need to specify Llama for one of the models. Here we can observe the difference in the responses. Let's ask another question, for example, about the largest mammal in Europe, in English so that both models can understand. We can see that Llama still struggles to comprehend the question, despite it being specific. On the other hand, the Alpaca model correctly responds that it is the brown bear. We can verify the accuracy of this response on the internet, thus we can easily observe the difference in performance between the Alpaca and Llama models. In this task, we will learn more about the Vicuña model, another model derived from the Llama model. Vicuña was developed by LocalAI and is a fairly recent model. The Vicuña 13b model is an open source chatbot trained through fine-tuning with web data. They used conversations shared by users, which were collected using the ChatGPT tool. In a preliminary evaluation where GPT-4 was used as a judge, Vicuña demonstrated in approximately 11 cases an improvement in the response quality compared to OpenAI's ChatGPT model and Google's BAR model. It even outperformed all the models of the same quality from Google. Specifically, in the case of Google's ChatGPT, the BAR model improved the quality of the response. Moreover, it surpasses its predecessors such as Llama or Stanford's Alpaca. Additionally, training Vicuña costs around $300, which is approximately half the cost of training the Alpaca model. The interesting aspect is that both the code and weights are available, along with a publicly accessible online demo. However, like all the models derived from Llama, its commercial use is limited. It can be used for research purposes, but not commercially. Therefore, we can say that the Vicuña model is the heir to the Llama models and may establish itself as a reference model based on the original Llama model in the coming months. If we visit the LocalAI's official page, the company that launched the Vicuña model, we can access the publication from April 28 of this year. It provides more information about the model, including its development, open source nature, functionality, and evaluation results. We can see that this model performs significantly better in most of the tests conducted on these chatbots. For example, it surpasses Alpaca and other models like Koala. It is worth mentioning that there have been recent variations of Vicuña. Here we can observe its superior performance compared to the GPT4All model. From this link, it redirects us to where we can obtain the weights, explaining the process of obtaining them. If we go to the beginning, we can explore all the products developed by LocalAI, such as Dream Studio, a data development tool. For further performance information, we can visit the LLMs page and search for the Vicuña model. Here we can already see that it is comparable to GPT-4 in terms of performance. They also provide access to the code, weights, and demo. What's interesting is that they compare it to previous models. In this case, comparing it to the Alpaca model, they ask both models to generate a blog about trips to Hawaii. We can examine the responses from each model and notice a strikingly different tone in Vicuña's response. It provides more details about the trip, uses colloquial expressions specific to the location, and talks about local food. This demonstrates that Vicuña's response quality is superior to its predecessors. To access this model, we can go to the official GitHub page. In this case, they suggest accessing it through the Fast Track platform, which facilitates easy installation of such models. Alternatively, we can use Hugging Face. In fact, on Hugging Face there is a chat section that allows us to directly access the Vicuña model. We can go to the single model section, select it, and choose between the 7b and 13b variants. The 13b variant has more parameters and thus performs better. We can then ask any question we want. For example, we can ask it to write a blog about trips to Europe and see the response it generates. With previous models like Llama, it couldn't even understand the question, and Alpaca had serious limitations when asked to write a blog, and able to adjust its tone based on our requirements. Here we can see how the Vicuña model, when asked to write an interesting blog, can modify its tone and writing style accordingly. Therefore, we can conclude that Vicuña is a highly useful model with capabilities similar to those of Llama. In this task, we'll explain how we can use an open source large language model from Flowise. To use an open source large language model from Flowise, the following steps must be taken. First, we must install Docker and Git. Once we have them installed, we will create a new language model. Firstly, we must install Docker and Git. Once we have them installed, We will create a local folder in the desired directory and access it from CMD. After doing this, we will use get to clone the local project within the following command. Once done, we will have the locally project locally and we can access it from Flowise. Next, we will download open source pre-trained models from GPT4All. On the GPT4All page, we can find various open source models that we might use. Simply download them from the page and then we will copy them into the models folder. After doing this, we will run the docker compose app Flowise command. This way, we will run the locally project we had downloaded. Once all this is done, we can access Flowise, generate a new chat flow, and add the chat locally command to use the open source model we downloaded. We can add this open source model. For this, even though we don't need credentials since they are not paid models, we do need to input the local path where the model is running and also the model's name. Now we will explain step by step how to do all this. The first thing we must do is install Docker. Docker can be installed for free from this link here. We would click download Docker and this would start downloading an executable, and we would have to follow the Docker installation steps. Once Docker is installed, we would need to install Git, especially to copy the locally project. Git is also straightforward to install. We would access this URL and install the Git version suitable for our environment. Once everything is installed, we would start by creating a local folder and then access it from CMD. To make it easier, we will create a local folder on the desktop. It would be this one here. And we will then access CMD. For this, we need to go up here in the path and type CMD. The CMD would automatically open in that path. The next step would be to clone the locally project with Git. This would be the locally project. It says here that it's an environment that allows access to different large language models. Here we will see its features, and in our case, we would need to access GitHub. This one right here. From here, we can access and get this URL, which will be cloned with Git. We copy the URL, go back to CMD and add the following command: get clone followed by the path we just copied. Here we can see how Git is cloning the repository and everything worked correctly. Now, if we access locally, we will see a series of subfolders created, and it's here, in models, where we will introduce the model we will download from GPT4All. So we will go to the GPT4All page, and if we scroll down, we will access the Model Explorer where we can see different pre-trained models. Initially, GPT4All had very few models, including the model called precisely GPT4All. We see that there are now many more models. This one is the GPT4All, and we have, for example, the Falcon, the Llama, and more models. In our case, we will choose this one here. We can also see that they offer a comparison of different models based on various evaluation metrics, and we can use this guide as a reference to download one model or another. To download it, simply select it and click here, and the download will start. This will take a while since these are quite large pre-trained models, so it will take a few minutes to complete the entire download. Once the model is downloaded, we will transfer it to the models folder within the folder we had created. And now we have to access the folder's path from CMD. We can access directly from here by typing CMD or otherwise from CMD using the cd command. Once inside the folder, we will use the docker compose command. However, Docker needs to be initialized for it to work. So we will access the Docker desktop application and initialize Docker. Once Docker is initialized, as shown here, and we have registered, we will run the command and it will start executing the Docker image. And now it would be running correctly. It will take a few minutes to load, and once loaded, we could use our large open source language model locally. This will take a few minutes to load, so we will leave it loading. and after about 10 minutes everything should be completed. The process will finish in about 10 minutes. It is important that during the process we go to the CMD and press enter several times to prevent it from locking up. Remember that loading the model might have taken between 10 to 15 minutes approximately. Once we have downloaded it, we are going to do a second test. Once loaded, the CMD will indicate that it has been created and initialized. In fact, if we go to Docker, we will see a new image named LocalAI indicating that it is running. Now we can access this open source model from Flowise and use it. Let's go to Flowise and generate a new model. We will go back to Flowise and create a new project. In this new project, instead of calling an OpenAI model, we will make a call to this open source model that we have running. We'll add an LLM chain and also prompt to pass instructions to the model. We'll use the prompt template since the basic instruction will be enough. Lastly, what we need to do is add the call to this local model. To do this, in the LLM section, under Chat Models, we will find the chat LocalAI. As indicated, it can be used for Granbury language models that are local, like Llama or GPT4All. We'll add it. Now that we have all the components, it is time to link them. We will link the chat LocalAI as a language model and add the prompt. In the prompt, we can add whatever instruction we want. Once the instruction is added, the only thing left is to configure the model. As we can see, we need to add a base path which is localhost/1 and the name of the model. We'll copy the model name, which we can obtain directly from the BIM file. We'll copy and paste it, but we need to add .bim, which is the model's extension. As we have mentioned, localhost/v1 will go in base path, and with that everything would be ready to test. We'll save the project as always before testing it. We'll assign a name to it, and now we can test it. The first few times the model might take a while to respond. Here we can see how they have given us different names for a car company and how everything works correctly. We would be using the open source large language model from Falcon that we had previously downloaded. And we can verify this because we haven't included any call to any third-party model like ChatGPT. Thanks to this mechanism, you can choose the open source model that suits you best and use it. The good thing about open source models, as we have mentioned, is that they operate locally, are private and also do not require additional costs. In this task, we'll look at a more advanced project where we are going to use an open source large language model locally. We will use an embedding model, also locally. In addition, these models will use information processed and contained in a vectorial database, specifically the Faiss vector database. The first thing we would need to do is program access to a large language model, thanks to the LocalAI chat module that allows us to use a model locally. These local models are downloaded, as we have already seen, from GPT4All, and we have different models available. For example, we can use the Llama 2 model, which is one of the latest updates from Llama and works quite well. We also have other variants, such as the one we saw from Falcon, which is one of the most recent and also performs well. There are also other models like Snorsys. At the top, we have a graph where we can compare the performance of different models. Once we have the model downloaded and saved in the models folder, we would need to use Docker to generate the image and start the model. Automatically, this model will link to the model if we pass the path and name of the model we just downloaded. The next stage would be programming the text processor. As we know, we need a module to load text information, in this case from a TXT file. For this, we use the TXT file module. It is also known that some models, or most of them, have a limit on the number of tokens they accept in context. For example, ChatGPT's is around the thousands, and the cloud model is about 100,000. Therefore, it is necessary to add a splitter that divides the text into different fragments, so we do not exceed the token limit allowed for each model. Finally, we would need to program the vector store database part. In this case, the Faiss vector store will be used with the observe module. Thus, when executing this process, the txt file will be processed, vectors will be generated, and they will be saved in Faiss. We link in the document section and in the embedding section. We link one of the local models we have in operation, in this case ADAS. Additionally, a storage path must also be provided to Faiss, as it will store the information locally. If we go to Faiss's information, we will see that it is nothing more than a library that allows working with vectors. Since it is a library that is installed locally, the storage of the indices will also be done locally, unlike other databases we had seen, like Pinecone, which are stored in the cloud. Once we have all these components and have linked them, we should add the conversational retrieval quad chain. This will allow us to use the local language model with information we added from Faiss, and will make it easier for us to interact with this model to answer our questions related to the information we have provided. Therefore, this would be a project in which we have used numerous components, from calls to local open source models, to introducing external information and storing it in Faiss's database and using a local open source embedding model. This would be the kind of project that a company might use if it wants to train a large language model with private data, which it does not want to make public, or for GDPR reasons are data that can be transferred. They could use this kind of project where everything is managed in a local environment and third-party proprietary models are not trained.